We talked about making pancakes. Now we're going to talk about making molecules. Same concepts. So the balanced chemical equation gives us the recipe for how the different reactants combine to make the products. Here we're looking at a recipe for ammonia. If you take 3 molecules of hydrogen and 1 molecule of nitrogen and put them together under the right circumstances, you can make 2 molecules of ammonia. That's the recipe, the balanced chemical equation. Just like we did with the eggs and the pancakes, we can pull out relationships from this balanced chemical equation. So if we had 3 molecules to 1 molecule to 2 molecules, we can also put that into dozens or moles of molecules, right? So we can get mole ratios from this balanced chemical equation. We can get the ratio of moles of hydrogen to moles of nitrogen. Well, looking at this equation, 3 moles of hydrogen react with 1 mole of nitrogen. So 3 moles of hydrogen to 1 mole of nitrogen. How about moles of ammonia? 2 moles of nitrogen. How many of these? 2. To how many of these? 1. So 2 moles of ammonia are formed for every 1 mole of nitrogen molecules that react. Does it make sense? If it doesn't, you need to ask a question. Does it make sense? Okay, shaking your head, that's helpful. Because sometimes we don't even know what to ask, right? That's the problem. We can combine any 2. Here we have 3 different things, right? We have hydrogen and nitrogen. Those are like the ingredients in the recipe. And here we have ammonia is like the product. So let me back up a minute. Did the pancake one make sense? Okay, good. Because if that didn't make sense, we need to go back further. So these are like the 2 ingredients. This is like, 3 eggs and 1 piece of bread are going to make, I don't know what you would make out of that, but 2 somethings. Okay? So 3 of this and 1 of that makes 2 of this. Okay? So when we write this over here, we're just taking the number in front of this formula, and basically we're inserting the unit moles. And that's an something else I did. Understood 1, and so there's moles in here, and moles in here. We could do that with dozens in the pancake recipe. We could say we get 5 dozen pancakes if we use 2 dozen eggs. You okay with that? So mole is the chemist's version of the dozen. So 2 molecules of this are formed from 1 molecule of that. That means that 2 dozen molecules would be formed from 1 dozen molecule, or 2 moles from 1 mole. Did that clear it up? Good. Question?
Why isn't it? Because there's hydrogen and nitrogen, and it doesn't be like, why is it 2 to 1? I don't get that.
Why is it 2 of these to 1 of those?
Yeah.
That's a good question. Well, if we look at the formulas, NH3, how many N's are in that formula, NH3? 1. In NH3, there's 1 N. In N2, there's 2 N's. And so it goes back to this picture here. We're going to make 2 of these from 1 of those, because this has 2 blue balls. And we can't have leftover blue balls. We have to use them. When we write the balanced chemical equation, there are no leftovers, okay? We also can't just have things appearing from nowhere. And so we learned that when we were balancing chemical equations. We can't just say 1 of these plus 1 of those equals 1 of these, because then we wouldn't have enough white balls and we'd have too many blue ones. Okay, so one of these is needed to make 2 of those. Now, in the recipe, you might have more stuff in your kitchen, right? But you're just choosing to use the right amount in the mixing bowl, because you don't want to throw in extra eggs and then have them be mixed in with your pancake batter. It's not going to taste very good. And so in our recipe here, our equation, we're just saying exactly what's needed. Is that better? Okay. Anybody else have any questions? Because this is a very important concept right here.
Maybe we can do more examples.
We will. Question?
Where are you getting the 3 mole H2
Okay, I'm getting the 3 moles of H2 right here. There's 3 H2s for every 1 N2. And we look at the picture, there's 3 of these to 1 of those. If the ratio is 3 objects to 1 object, the same ratio would apply for dozens, right? 3 dozen to 1 dozen. I'm going to use a different dozen, the mole. Remember, the mole is just a funky number of things. It's just a crazy big number. But it's Avogadro's number times 3 of these guys will react with Avogadro's number times 1 of that. Does that help? There's understanding, and then there's understanding how to do the problem. And you can actually understand how to do the problem without thoroughly understanding everything behind it. So that's kind of good. The just understanding how to do the problem is, let me do another ratio here. So we have 3 things here. Pick 1 to go on top. Somebody yell it out. Nitrogen. And 1 to go on the bottom, not nitrogen. Hydrogen. Okay, so if I need the ratio between moles of nitrogen and moles of hydrogen, I'm going to go over here and erase this. Let's clean it up a little bit. I go to the balanced chemical equation and I look for the coefficients in front of those formulas. There's a 3 in front of the hydrogen. So then I put a 3 in front of moles of hydrogen. There's an understood 1 in front of nitrogen, so I'm going to write 1 nitrogen. I can do any 2 in a ratio. Question back there.
So then you can do, like, maybe 2 moles of N3, the first one, and the 1 mole of nitrogen.
Mm-hmm.
Could you do like 3 H2 to 2 moles?
Absolutely.
Oh, okay, so
It can be anything.
oh, okay.
Okay? No. So 2 moles of ammonia. And see, when you guys ask questions, that's really helpful to me because there are things I overlook because it just makes so much sense to me. So I could do 2 moles of ammonia to 3 moles of hydrogen. You can take any 2 of these. And if you had 6 reactants and 17 products, you could pick any 2. They can both be reactants. They could both be products. It doesn't matter which one you put on the top and which one you put on the bottom. Because like we did here, this one is just upside down of that one. The beauty of this is converting moles of one thing to moles of another, it's always one step. And the conversion is always in the balanced chemical equation. So that makes it really easy. Any other questions? Yes?
On the homework, we probably might get to this a little bit later, but on the homework, I remember that there is a question on there that it says, like, how many conversion factors can you make from the equation given above? So is it kind of somewhat like?
That's one of those good exercise problems to make you think, right? So, yeah, obviously I can make at least 4 here, but there's more that I could make. And so you just kind of have to do trial and error because this one and this one are upside down of each other. I've got this one, I could also flip that upside down, that's another. I could flip this upside down, and then you have to look real carefully to make sure, did I cover everything? I will not do that on an exam. Yeah. It's a good question. It makes you think and investigate, but I don't think it's a good thing to test on. A good thing to test on is, do you know how to make the one that you need, and do you know how to use it? Okay. Any other questions? So, sticking with this formula, this recipe for ammonia. If we have 3 moles of nitrogen and plenty of hydrogen, how much ammonia can we make? This is like the 8 eggs problem, how many pancakes? And we're going to approach it in exactly the same way. We have 3 moles of ammonia. 3 moles of nitrogen. 3 moles of N2. And what are they asking us for? How much ammonia? So we're looking for moles of ammonia. This is how we choose which of the many conversion factors are available. It's the units. So we're starting with moles of nitrogen, and if we want to write a path, it's going to be moles of nitrogen to moles of ammonia. That's our path. This is what we're given. This is what we need to find. Always one step for these. So, moles nitrogen to moles ammonia. Moles nitrogen to moles ammonia. And then in the denominator, I'm going to put this unit so it goes away. This is that dimensional analysis pattern or technique that we learned. You put all the units in, get them to work out. Then you look for numbers. We don't have to look very far. They're in the balanced chemical equation. Here I've got ammonia, NH3. I find NH3 in the equation. It's got a 2 in front of it. So I write a 2 in front of moles of ammonia. In the denominator, I have moles of nitrogen. I find nitrogen in the equation. It's got an implied 1. I'm going to write 1. Does that make sense? Just like what we did with the pancakes. But when it's moles of nitrogen and hydrogen and stuff, then people go, I don't know. So numbers, 3 times 2 divided by 1, we can make 6 moles of ammonia. Any questions about that one? Let's do this one. How many moles of nitrogen are needed to completely react with 7.13 moles of hydrogen? This was all nice whole numbers. This is not a whole number. Well, let's write our path. We were given the number of moles of hydrogen, and the question asks, how many moles of nitrogen? So that's what we want to do, moles of nitrogen. Now I'm going to write out my equation. I have 7.13 moles of hydrogen. And what unit do I want in the numerator? N2. So I have this, and I'm trying to go to that. I have this, and I'm going to this. This is like the path, Dora and the map, and they chant. Moles of hydrogen to moles of nitrogen. Moles of hydrogen to moles of nitrogen. Then this unit I need to divide by to make it go away. Moles of hydrogen. So I get all my units worked out. The numbers come from the chemical equation. I go up here and I find nitrogen. The number in front of nitrogen is a 1. And I find hydrogen. It's got a 3 in front of it. So I'm going to write 3 in front of moles of hydrogen. Calculator. Upside down and backwards calculator. 7.13 times 1 divided by 3. And I lost the tip of my stylus. There it is. I'm just falling apart today. My calculator says 2.376666666666. Repeating. Now here's a question. Significant figures. 3, that's correct. So this should be 2.38 moles of nitrogen. These numbers are exact. Okay? Because this equation describes the number of atoms that react. It takes exactly 3 molecules of hydrogen to make exactly 2 moles of ammonia. Because it's particles. There's no question. At its basic level, it's counting small numbers, and so those are exact numbers. So whatever you're starting with, that's what you're going to end up with. We started with 3, we end with 3 significant figures. Any questions? So water forms when hydrogen gas reacts explosively with oxygen gas. Here's the balanced chemical equation. So we have oxygen reacting with 2 hydrogens to make 2 waters, okay? This is why we had to learn how to balance chemical equations, because if you have one that's not balanced, we need to balance it before we can do problems like this. Here's the question. How many moles of hydrogen oxide, how many moles of water? I don't know. How many moles of water result from the complete reaction of 24.6 moles of oxygen? Assume that there's more than enough hydrogen. Okay, when we're doing a problem like this, these are still pretty simple. They're going to get a little more complicated. I like to use the balanced chemical equation to organize the information that I've been given. So what I'm going to, that's why I left a blank here, so I can write. So how many moles of water? That's the question. So under water, I'm going to write question mark moles, because that's what I'm trying to find. And then here it says 24.6 moles of oxygen. So under oxygen, I'm going to write the amount that I've been given. 24.6 moles. And so that just helps me to see what I'm doing. So I have this, and I'm trying to get that. That's going to be my path. So now I can just write it out and get the units in. 24.6 moles of oxygen. My path says moles of oxygen to moles of water. I want moles of oxygen to go away, so I write moles of oxygen down here so the units cancel out. You have to write the chemical formulas because moles of oxygen and moles of water are not the same thing. And so you can't just cancel moles without knowing moles of what? What number should I put in front of moles of H2O? 2. And in front of moles of O2? 1. That came from up here. One of these makes 2 of those. So now we just do the math. 24.6 times 2 divided by 1. And my calculator is telling me 49.2. My initial number had 3 significant figures. This one has 3, and so we don't need to round or do anything else. I can make 49.2 moles of water. Any questions? Does that make sense? Good. Because this is the central part of stoichiometry. This is the middle part. And then we're just going to add on to the ends a little bit.